For today's lecture, I'm going to try another impersonation. I was really contemplating who to do for the impersonation, and well, I think there's three conditions you really have to consider when you're going to do an impersonation, and one of those would be, well, how well known is your person, and you know they can't be like so well known that it's obvious right away who's going to be. So, like for example, Donald Trump or Arnold Schwarzenegger, that wouldn't be any fun. So, those are ruled out of the window right away. But another possibility or another problem would be that nobody knows who your person is. So, well, then it's no fun either. So I like to think, or at least there should be a reasonable probability that you know who this person is. At least some of you, maybe not all of you. Well, those are the first two conditions. So not too popular, but not too unpopular, if you will. And well, the third condition would be that, well, can you do the impersonation with reasonable levels of competence? And well, I'll let you guys be the judge of that. I do see in the chat that Kermit has been guessed. Well, some people have claimed I am intellectual Kermit the Frog. However, that is not correct. Well, Mr. Van is another good guess, but no, not quite. So, well, without any further ado, I'd like to go through the next 10 slides or so. So, continuous distributions. So, continuous distributions are a lot like discrete distributions, which we just discussed earlier. But continuous distributions, just like discrete distributions, they graph the possible values of x versus the likelihood of occurrence, probability of x. So at least we have some commonality there. But here's where they're different. Discrete distributions can take on an infinite amount of decimal values within the particular domain of possible x values. So we did discuss this a little bit earlier, but just as an example, I'm going to sort of elaborate on this, I suppose. You could say, if x represents waiting time for the next customer, then x is a continuous random variable. And, well, what does that mean? Well, for one, the probability of getting an exact value of x no longer makes sense. Well, you could say, well, what's the probability that the next customer arrives in 4 minutes? And maybe you'd say, well, the probability I think would maybe be about 10%. Well, you'd be wrong. And let me explain why. Well, I guess in the general sense of 4 minutes, you might consider 3 minutes and 56 seconds, or let's say 4 minutes and 4 seconds to be 4 minutes. But let's just say, for the sake of argument, that you're saying exactly 4 minutes, as in 4.000000, etc. You get the idea. Well, what's the probability of getting that exact time? Well, that would be essentially impossible. So the probability of getting an exact value for any particular value of x is 0, which is absolutely mind-boggling to think about because, well, I'll get into that later. But just know that the probability of an exact value, it's not possible. So that's something to think about, at least for now. So what's the use of continuous distributions if you can't figure out the exact probability? Oh, well, I won't say the answer to that, the one guess there. So, well, we'll get to that later. So I won't say yes, or I'll play the fifth on that one, I suppose you could say. Instead, the probabilities can be calculated by measuring the area under a curve with a specified interval. So now we have something concrete. Now we got something we can deal with, practically speaking. So this is how you write the notation. Just got to know the notation a little bit. P bracket 3 is less than x less than 5. All that means is I want to find the probability that the next customer arrives between 3 and 5 minutes. Now I've got something we can actually handle. Now we've got something. So that's how you want to think. Okay, so I would like to use an example using a histogram. In a previous lecture, we talked about histograms a little bit. So you can represent continuous distributions using a histogram. You could think of it kind of as your key from the continuous world into the discrete world, in a sense. Each bar represents a specific range for X variable. You could call them classes. So you can think of it somewhat like a hierarchy, like a dominance hierarchy of sorts, if you wish. And you're splitting it up all into classes. So you could think of it a little bit like Marxism, but Marxism is very bad. So maybe we shouldn't go there, I suppose. So let's look at this histogram just as an example, and we could see height on the x-axis and on the y-axis, the number of students that have that particular height. And we could ask a question like, well, 3 people have, or what's the probability of a particular random student chosen having a height between 48 and 50 inches? Well, you can see right there that 3 people in this survey of students have that height range, somewhere in that height range. So you could say, oh, this is kind of in the way here. Let me get that out of there. Well, that 3 people out of the 42 in the survey have that height range between 48 and 50 inches. So the probability of having that height range between 48 and 50 is 0.0714. So that's something we can practically deal with. Hopefully that makes sense, but let me know in the chat if you have any questions per se. Okay, let's move on here to a couple of specific examples of continuous distributions. And I put here, I did leave out one of my favorite distributions, which I have a whole slide for my favorite distribution later on. But for now, let's look at the normal distribution on the right. Every distribution has a formula, a probability distribution, but you can see that f of x there. It's a little bit technical in how we interpret that, but you can see on the right, the normal distribution, well, it's bloody complicated, man. You do not have to memorize that one for the test, so you don't have to worry about that. But I think there's something to be said about just the elegant beauty of that formula. So take a moment or two to admire it, I suppose. So you can see another important thing about these distributions is you see that they're represented by a histogram. And if you sort of do a frequency polygon through them, you generate the theoretical distribution. So distributions are very theoretical, whereas histograms, they should approximate in a sort of way the theoretical with the sample size sufficiently large, of course. So on the left, you have a much significantly simpler distribution. You have their uniform distribution, and that just simply means everything within the particular domain is equally likely. So we have equality in the strictest sense. And, you know, with sample sizes vary, you might not have an exactly straight horizontal line. There's a little bit of give and take with the randomness of the nature, but generally speaking, you should have a horizontal line. So, and then the one on the right, I'd like to elaborate on as well, because it comes very close. It looks very similar to one of the ones that I really, really like. It's the exponential distribution. Exponential distribution, well, we'll do an example like that as well, but it's a very skewed distribution, as you can see. So, and it has a formula as well, as you can see. And you don't have to worry so much about those formula. You don't have to memorize them. That's more of a technical detail. So hopefully that's a sufficient explanation for, well, a very brief introduction, at least, to continuous distributions. Now we're going to look specifically at the examples and how you might solve some probability questions. But before I do that, I just wanted to say, I almost forgot about this. The area under a continuous distribution must always, no exceptions, always total to 1. And this, at first glance, is something that is entirely obvious. It seems pretty clear. Something has to happen. But then if you think about a little bit earlier, I said the probability of an exact particular value of x is 0 or infinitesimal. But then you think, well, something has to happen. So we got this paradox, man. And that's something I just don't know the divine significance of it. It's something that boggles my mind. So, well, I don't know. You can think of it as you will, I suppose. But me personally, it really boggles my mind. So let's, without further ado, go over a couple of examples on these distributions. Well, suppose you want to pick a random number between 0 and 10, and all those values are equally likely. What's the probability that a number is larger than 7? Well, you might start by drawing the distribution, and it's uniform. So that's pretty easy to do. You just have to draw a horizontal line like so until you reach 10. So this is just some simple elementary level geometry. So we know the total area of the rectangle has to be 1. We just talked about that. So that should be fairly straightforward and self-evident. What must the height of this rectangle be? Well, you know that the area is 1. And you know the area of a rectangle's length times width. So the base is also 10. So then it's just a simple algebra that you have to solve. And 1 equals 10 times something. Well, that would give us a height of 1/10, or in other words, 0.1. So that is the formula for this distribution. It's simply f of x equals 0.1. That's it. So maybe I went ahead too far there. What is the probability that the number is larger than 7? Well, that would just be the area of the red rectangle, which we can very easily calculate using grade school length times width. Fairly straightforward. 3 times 0.1 in this case. So yes. So let me know if there's questions on that. Okay. So without further ado, let's go to the next example. Exponential distribution. So a lot of times wait time can be exponentially distributed, and at least it can be approximated as so. So the average wait time between customer arrivals in a coffee shop at 10 a.m. is 2 minutes. So the wait time is distributed, and you don't have to worry about the technical details of how we got this formula, but the formula is 0.5 e to the power of negative 0.5 x. So that's f of x. And again, it's not representative of a probability per se, although you could put in inputs of x and compare them, and that gives you a relative idea of how more likely one is than the other. But in terms of finding the probability using this formula, it's relatively useless. But all is not lost in terms of answering questions. One thing that we might ask is, well, what's the probability that the next customer will come within the next 3 minutes? Well, how do you go about doing that? You can't use the formula, that's for sure, because, well, the formula just gives you the height, but we want the area. So in specifically, we want the area between 0 and 3. This is not a simple rectangle anymore, per se. However, if you wanted to estimate the area, you could use rectangles, and that will give you an approximation of sorts. So you can see that on the screen. Those are rectangles. And what if you figured out the area of all those rectangles? That's a pretty straightforward calculation, as we've seen in the last example, but you just have to do it 6 times with 6 different rectangles and add them all up. Very tedious. So do you want to do that all the time? Wrong. You have to do it. There's a much easier way, thankfully. So you can use calculus, and don't worry, because we'll just sort of take this fact for granted. I know none of you taken, some of you that are taking calculus with me at the same time, well, we haven't covered this topic yet anyways. But just take this, that there is a way to figure out the area under the curve from 0 to x. So, and you can see in the green there, so that formula actually tells us the area of getting less than a particular value. And calculus can help us with that. So don't worry about the technical side of those things. So calculus gives us essentially a way to make infinitely small rectangles to calculate the area under the curve of interest. And that's what basically is happening. So what you would just do is simply plug in x equals 3 into that formula, and you can use your calculator, and you get 0.777. So capital F of 3 is what we use. And that just is a way of saying the probability of getting less than 3 minutes, or I guess I should go to the example, a probability that the next arrival is within the next 3 minutes is about 78%, and roughly speaking. So that's something, I suppose. So let me know if there's questions on that. Okay, I think we're near the end here. So just a few last points on different distributions. I believe we've seen something similar to this earlier last week, but just as a reminder, we could have positive skew data, and that would be a situation where the majority of data falls below the mean, a minority of high values skew the average. I'm actually going to talk about one such positive skew data, one of the most important ones, I think, in the next slide. But income distribution, that would be a textbook example of this. And negative skew, the majority of data falls below the mean, but a minority of low values skew the average. So perhaps an exam score might follow that. Not always, but perhaps. And then, of course, we could have normally distributed data as well, which we'll talk about a lot over the next few days. You could also have bimodal distribution. Sometimes that happens, actually. Sometimes test scores tend to follow that because, either you know it or you don't. So that's that. Well, yeah, Jordan Peterson, that was correct. Julia got that. I don't know if anyone else is familiar. I know a lot of you maybe have not heard Jordan Peterson before. If you have not, he actually talks about this Pareto distribution a lot. So if you want to know how close I was, there we go. The Pareto distribution, just a little bit of an intuition behind that. Well, this is, for example, wealth distribution. You may have heard it said something like, well, the top 10% of a particular country hoard 90% of the wealth. That would be a typical example, but this is not just true for wealth. It could be true for any sort of particular domain. So, for example, goals scored in hockey, or books published in a particular topic, or the example on the right there, traders in a particular trade. Or maybe people who do Jordan Peterson impersonations. You could have many people who try to do impersonations, and they're lousy, but only get a few very successful ones. So that's that, I suppose. So hopefully you enjoyed my impersonation, and maybe you have other suggestions for me in the future. So, well, that's that.